I'm going to try and record as best as possible. I didn't get a chance to record during first period at all, so I want to make sure that we do here. So, if we continue our discussion from last week, what was the goal of the lab with the M&Ms that we did on growth and decay? Growth and decay. Now, remember, you had something that you calculated. This is where you have to refer to your lab during class, so I have it out for you right now. Look at your lab. On the first data table, remember you calculated the growth factors? Remember all those growth factors? What did the average become through your growth factor for the first table? Give me some samples. 1.5. 1.5. 1.5. 1 point what? 1.3. Okay. All these numbers like 1 point something, right? Yeah. They seem to be okay. Now flip to your third table where you have decay now, or your third page rather. Sorry, which is the table for decay. And you're going to notice that what were those growth factors?
0.53.
0.53. What do you got?
46.
46. 54. Okay, those are all decimals, right? Between 0 and 1. You notice that?
Yeah.
So if you think about it, we can make, to start right away, we can start with our easiest thing to look at is this first part. We have the general or standard form of the function. And remember H and K, where are H and K still?
Right.
Vertical and what?
Horizontal.
Horizontal what?
No.
Shifts. Shifts. Remember? Slide to the right, slide to the left. Those are your shifts. Okay? So H and K are the shifts. If you remember from our lab, A was the value of the starting point, or how many M&Ms we had to start with. So if we had one M&M to start with, like we did in the first part, A was just 1. And then on the next part, though, didn't you start with like 150 M&Ms and it decayed over time? Yep. By that time, A was then 150, whatever that was. So A is really like my starting point. And then the B value here, the B value was my growth factor that we had in the problem. So this is all recollection from what we did in the lab, but now we're going to actually discuss how it works. So here's what we can write, and you have this already in front of you. You should all have this written down already, so we're just going to read through it together. And I'm going to make some suggestions on things you might want to write additionally. So what I'm doing now is annotating. That's what you should be doing also. So stuff that I add on or stuff that I say that you might want to write on those notes that are worthwhile. So first of all, B tells us if it's growth or decay. If B is greater than 1, if you didn't know what that meant, you should write that in words. That's a greater than symbol. So if B is greater than 1, then we have growth. What does that next part say? Because so many students get this confused. How would I read that?
Less than B, less than 1.
Good. If 0 less than B less than 1. Now tell me in words, somebody raising their hand, what it actually means. How would you actually say this? If 0 is what? Or if B is what?
If B is greater than 0, less than.
So what does it mean? It's where? Where is it located? What's bigger than 0 less than 1? Or just, what was the term you used? In between, right? Somewhere in between, right? So what we can say really is when B is between 0 and 1. That's what's really going on here. Because a lot of people get confused. They look back at their notes and they see this notation. But they don't recognize that what that means really is that B is between 0 and 1. It's somewhere between 0 and 1. Okay? Now, can it be 0 or 1?
No.
Why not?
Because it doesn't have the slash.
Well done, sir. Again, if it had a less than or equal to sign for both of these, then the endpoints would be considered to be included, right? It could be 0 or 1. But because it doesn't have a less than or equal to, like those two slots right there, I'm going to take both those off because I don't want to confuse people. Because it doesn't have those there, we cannot include the endpoints, which makes sense because we're going to see today that if B is 0, this just becomes 0 right here, and this whole thing drops off to 0. And you don't have growth or decay. And if B is just 1, this is just a 1 now. And 1 to any number is still 1. So you don't really have growth and decay there either. So B is never going to be 0 or 1 for growth and decay. It's going to be between 0 or 1 for decay and greater than 1 for growth. Again, greater than 1. So 1.1, if B is 1.1, it's growth. If B is 1.0001, it's growth. But if B is 1, it's neither growth nor decay. Okay, we're not going to have a function there. Well, we'll have a function, but it's not going to be a growth or decay. So remember, the important part is to know that B tells us if the function is growth or decay. Easy enough? Okay, easy enough here?
Yeah.
Next. A represents the original, and I put quotes around that for a reason. Remember in the lab that we did with the M&Ms, the A value was the starting amount of M&Ms. So either the growth one would start with 1, and the decay part would start with however many you have. But now, if you remember, come on, finish off whatever you've been doing over there for a while. If you remember, H and K represent translations. So now, if there's an H and K, the y-intercept is going to move. It's going to be translated. So I'm putting original in quotes because it might move if there's a translation. Again, it might move if there's a translation. It also dictates, what is this word here? Concavity. And don't think of a cavity in your tooth, but, well, actually, you can think of a cavity in your tooth, actually. There is a good explanation for that. But have you heard the term before? Concave?
Yeah.
What does that have to do with it?
Slope, right?
Good. The slope or the curvature, we'll say. The curvature, the shape. What other class have you heard the word concave in?
Geometry.
Geometry for sure. Very good. Good concave or convex polygons. Where else? There's another class besides math, outside of math.
Science.
English maybe, but science. Where in science do you hear concave and convex? Is there science or physics? Either one. More specific. What do some of you guys put in your eyes or on your eyes every day?
Contacts?
Contacts or yeah, sometimes you have to, yeah. Contacts or glasses, right? Don't you have a lens? Isn't that lens kind of bent? Is that how it works? That has to do with the concave or convex lens. So the term concave means that it's some sort of a curvature, okay? Some sort of curvature. So if I think about this, and I didn't go into much detail in this class about it, so I want to make sure I do. This is something that's concave up. Because the curvature, which way does it open? Up. Something concave down would be what?
Down.
Show me with your hands.
Oh.
Thank you. It's just going to be that. That's all it's going to be. Okay, so that's going to be concave down. So the easy way to remember this is to look at the curvature and say to yourself, and I was saying this in class the other day, if I were driving on a highway and I wanted to take the inner lane, right? The inner lane, and this was the highway. Isn't this the inner lane here? I'm taking the inner lane around the loop. And the inner lane is above or up or above. This is concave up. This inner lane, though, if I were driving, would be on the inside here, wouldn't it? Wouldn't that be the inner lane, and that inner lane, and that would be below it or down. So this is concave down. So we have concave up and concave down. Okay? So this A value is not only going to tell us about the actual function itself and where its y-intercept is, but it's also going to tell us about the curvature. The curvature. If you, yes?
Is that another way to say parabola?
I wouldn't use the word parabola. Parabolas are easiest example, but what I was about to show you might answer your question. Watch. Remember the other day exponential growth looked like this? And exponential decay, it looked like this? These are still both concave up, though. Because look at the curvature. If you continued this curve, right? See the curvature? It's pointing like upward. This one is pointing upward and out, but it's still pointing upward, right? Whereas if I drew a graph that looked like this, for some reason, say I was doing a square root function. Remember the square root functions? That's concave down. Okay? So that's what down means. These both mean up because they're both pointing out or upward. So a parabola is a good example of it. But concavity is the term you want to use. Concavity, if you want to write down a definition, just write curvature. Okay? Curvature. Okay, so growth and decay happen to both be concave up. We're going to see today when growth and decay are not concave up what happens, and we'll talk about that.
Straight line.
You could have a straight line, and then there would be no concavity. A straight line has no, think about it, does a straight line have any curves to it? So its concavity is non-existent. It has no concavity. Okay? Not concave up, not concave down. It's like neutral. Okay, like a positive and a negative, electron and proton, or on a battery. If you combine, you get neutral, like a neutron. Okay, it'd be neutral for a line. Like Jimmy Neutron, yeah. Again, H represents the horizontal shift. The last part, though, is interesting. K represents the vertical shift, but you're going to see in parentheses that term. What does that term mean in parentheses there?
Also as horizontal asymptote.
Horizontal asymptote.
It will never touch it, but it will get very close.
So can you come up and draw an example of that?
Sure.
Wait, show me an example of any graph, doesn't matter, whatever you want, that has a horizontal asymptote, and show exactly what you mean by it's never close but never touch. You can open a new page if you want, because we're done with this notes here. Want to just do that so you have the whole page. So it doesn't matter what it looks like, as long as there's some sort of a horizontal asymptote somewhere. Bam. Okay. Bam. I see what you're doing.
Yeah.
Can we? I think you were good until you started coming back up at the bottom of the C, though, because it's not going to come back.
Yeah, I didn't. Yeah.
So let's just erase the bottom of that C and make believe that didn't happen. So it just got closer to the x-axis there, right?
Yeah.
So let's get rid of keep going a little further, a little more. Too much.
Woo.
Okay. So that bottom loop of that C value, and again, this would not be a function. It doesn't pass the vertical line test. But the bottom part of that gets closer and closer to the x-axis. So the x-axis would be like an asymptote. Okay, a horizontal asymptote. Thank you, sir. Okay, so we're going to see that for these graphs, we have a lot of horizontal asymptotes. We're going to have a horizontal asymptote like that. We could have exponential decay that's getting closer to this horizontal asymptote. It could be exponential decay that's getting closer to the x-axis. So the x-axis is now your horizontal asymptote. So the asymptote can move up and down. The asymptote can move up and down because we have a value of k. And k represents the vertical shift of the graph. Okay, the vertical shift of the graph. All right, let's go on and let's take a look now. So let's look at the bottom box on the page. Here's what I want you to do. Partner up with somebody that has a calculator if you don't have one. If you do have yours, though, please take it out. And what I want you to do is only start by just drawing a sketch of each of these. And what I want you to do is the following. Draw the sketch mainly for the two quadrants of the quadrants 1 and 4. Okay? These are what I want your axes to look like. Draw a quick sketch of each of these, please. Draw a quick sketch of each of them, and we're going to discuss that. So if you don't have your calculator, you're looking out at somebody, and you're doing this together, and you're doing the y equals. Now, it might help to turn off your plots. Okay, remember the other day we had the plots on because we were doing the stats?
Oh, yeah, you right.
Okay, so go to y equals, go up to plot 1 and turn it off. Again, hit y equals, go up to plot 1 and hit enter to turn it off. Then in y1, you can simply type in the first equation, 2 times 2 to the x. Okay, and again, you're welcome to hit zoom 6. If you hit zoom 6, you might see the graph a little bit better. Okay? So if you want to hit zoom 6, you'll see the curvature of the graph. Yes, and just hit zoom 6. Everybody hit zoom 6, just so we're all on the same page when we're doing this. Okay, we can zoom a little bit further, that's fine too. We're going to try and turn off our plots like we said. Alright, we follow directions. And I press zoom 6.
What's a window range?
Again, turn off your plots and press zoom 6. It's very much so the second one, down, change the brightness of the
Do we like sketch it?
Do you like sketch it? That was the question I just heard. Do you like sketch it? What do you mean? What just happened here, guys? Anybody?
Your screen just went off.
No, the smart board. Does this happen a lot in this room? Yeah, I moved the laptop. It's not a screensaver. The lamp went out. Does this happen periodically?
I don't know. We don't use it really.
I never know.
We should move the cable.
No, I mean the bulb went out, guys. Like, look, there's no projection at all. It actually turned off.
What about
The gray light is
restarting?
still on.
Yeah, I'm about to say, what about restarting? First cut.
You got all 4 sketched so far?
Yeah.
Make sure you use your parentheses when you're putting in fractions.
Hey, Jordan,
Excuse me, sir.
you mind being quiet?
No, I don't. Yes. You're gonna be good. Yeah.
Thank you.
All right, smart boards we're starting, guys. Let's see if this works or not. If not, I'll record during 7th period. When that stops blinking red, if somebody sees that stop blinking red, let me know. All right, so what you're going to notice for this kind of a problem is you're going to get 4 different graphs here, right? They're going to look similar, though. And you're going to notice some similarities between the top and the bottom graph, and then the left and the right graph also. So again, all you're doing right now is just sketching these 4 graphs. Just a quick sketch, that's it. Okay, a quick sketch. Most of you are almost done, I see that, good. Usually flashing red is not good, right? Xbox? Who's Xbox? Ring of Death?
The death of rings?
Ring of Death, isn't it red?
Ring of Death, yeah.
I got the Ring of Death on the smart part right now.
What? Right there.
Oh, it's the ring of death.
Never mind.
What you doing now?
I ain't never got that. I'm gonna go home and get it.
I know, sir.
I left my Xbox.
I got it before.
Somebody already mentioned to me that this board is a little bit faulty, so.
My Xbox.
We're back to green.
Purple
Oh, Grandma.
and orange.
How do you win that?
Blue and green make
You know what it is? I guarantee you, the lamp probably overheated and it turned off for a safety feature. Yep, it's back on. Okay, it'll work hopefully. Let's give it a minute and we'll be able to get back on. It's still recording, which is fine, so. No, always
So they're
awesome
gonna hear all
comments.
this.
Alright.
All right, come on, loading up. There we go. And we are back. All right, let's do this. So, the first thing you noticed, right? This one, it simply, if you just sketched it, looked like that, right?
Yeah.
The next one should look like this.
Yeah.
The next one should look like this.
Yeah.
And then the final one should look like this.
Yeah.
So we have our sketches. Let's discuss now. Let's talk about this. Because it's easy to recognize this. And what I really want you guys to be familiar with are the properties of exponential functions. You have your calculator, so you can always graph on that. So graphing these is not as important, really, but it's understanding them that's important. That's where your quiz is going to go out. Your quiz is going to be able to actually answer a question based on the graph. Something about the graph, something about the data. Or maybe even like match up a function with the graph given. So I can show or see that you have a complete understanding. So we're going to be, what we're going to do now is just discuss and describe the graphs. So first, you see the term positive growth? What does that mean? If a number is positive, give me an example.
1, 2.
2, 1, 3, any of those. It's growing, so it's getting what?
Bigger.
Bigger, right? It's getting bigger, it's growing. Well, what is this term negative growth at the bottom then?
Negative.
Smaller.
-1.
It's getting smaller, sure. The number is getting smaller, it's getting more negative.
Below the
But what about its absolute value? What's happening to that?
It's getting higher.
This thing is.
It's getting higher, getting bigger. Let's discuss real quick. Let's take a look. Here, this would be like -1, right? Then like maybe like, I'm doing the y value, sorry. -1. Let's say this is like -2. This is where -3 is over here. It's getting smaller, the number, but its absolute value is getting bigger. It's going 1, 2, 3, so it's still kind of growing, right? But it's growing in what direction? In the what direction? Negative, thus negative growth. Again, think about this for a second. This value or this function is growing. It's getting larger in the positive direction. So we call that positive growth. This is still growing, but it's just growing down. Believe it or not, again, look at it. It's growing, it's getting further from the x-axis. It's growing, but it's growing downward. Okay? Now, take a look and notice. This was concave up, wasn't it?
Yeah.
And look at the a value, it was positive.
Yeah.
And now look at the next part.
Negative.
The a value is negative and it's
Is it a reflection?
concave. That's exactly what it's like. Very good. It's like a reflection over the x-axis. Very good. Remember, when you negate an entire function, you're reflecting it over the x-axis. And we've negated that by putting the -2 in the front. Only.
So we just did a conjecture.
Yes, we came up with a conjecture. Absolutely.
If the growth is negative,
It's either gonna, no, if the growth is negative and concave down, it's gonna be going downward.
Very good. It's going to be, what's the word you're looking for there?
It's just gonna decrease?
It's going to decrease. Whereas when it's a growth that's positive, it's going to
Increase.
increase. These are terms that you're going to see in pre-calculus and in calculus over and over again. Concavity, increasing, decreasing, okay? All those terms. You'll see them in statistics also if you take statistics. You'll hear about increasing and decreasing, what that means, okay? Next, on the right-hand side now, we have decay, and we saw this in our lab, didn't we? We saw this one right here in lab. That's the one that we saw with the M&Ms. It started with like 150 M&Ms, and then it went down over time. So we have decay, clearly. I call it positive decay because, personally, look at the numbers. Aren't they above the x-axis?
Yeah.
So when you think of them as positive, that's one way to think about it. But the other way to think is, again, the value of A is positive. So it's concave up. Whereas here, look at the value of A. It's negative. And look, isn't it concave down? It's pointing down again. So this is positive decay. This is negative decay. Okay, this is negative decay. And take a look. Positive decay, it's decreasing because it's, again, look, it's going down like that. But negative decay is actually increasing because look at the function. It's actually moving up along the y-axis. So it's an increasing function. Okay, it's an increasing function. So our parameters are what are important. If A is greater than 0, like this, and like this, when A is positive, it's concave up. And we said that already. When A is negative, it's concave down. Next, if the B value is greater than 1, we have growth. It can be positive or negative growth. When the B value is a fraction or a decimal or some value between 0 and 1, we have decay. And it can be positive decay like we've seen, or the reflection of that, which is called negative decay. Again, notice these two are really like reflections of each other, as Ebony said a minute ago, just as these two are reflections of each other. By the way, one of the simplest or age-old problems is called, oh gosh, the trumpet problem in calculus, where they take a volume of two curves and they prove that there's a limit to the volume but not the surface area. Okay, I forget the name of it. I'll look it up. I'll put a little link to it on Endline tonight. But one of the problems is that one of the age-old problems that we've seen in math is positive decay and also negative decay at the same time. And think about the shape that this creates. If you connected it, it would create like a trumpet, right?
Oh, it's right there.
Oh, it's trumpet.
I know it's hard to see, but that's the horn of the trumpet. Somebody's playing a trumpet. Here's all the keys to the trumpet, right? And then, here's the mouthpiece on the trumpet at the end. And then here the sound comes out of the trumpet like that. Forget the name, but it's somebody's trumpet. Gabriel's trumpet, or Gabriel's horn. Gabriel's horn, Gabriel's trumpet. It might have a reference to it, I'm not sure. I'll look it up and I'll put a link to it though for sure. Anyway, the idea though is that we have four different types we're going to look at. Positive growth, negative growth, positive decay, negative decay. One other thing that somebody pointed out in first period that I didn't even notice right away was this. Look at the words. Positive, you think obviously positive. When you hear the word growth, don't you also think about positive when you hear growth?
So it's going to the right and it's going upward.
Positive tells me that it's going right and up, which is considered to be increasing.
Yeah.
Increasing. Plus times plus gives me a plus there. Next. Negative growth. What's a negative times a positive?
Negative.
And doesn't that make sense? Now it's decreasing.
Yeah.
Decreasing. Look at the next words over here. We have negative decay. I think of negative, right? But what's a negative times a negative? A positive. Thus, this one is actually increasing because it's positive. Up here, positive decay. Isn't that what you think of? What's a plus times a minus? A negative. And take a look. Isn't that one decreasing? So if you look at the words and assign them some sort of positive or negative sign and actually multiply them, you can actually determine whether it's increasing, decreasing, or increasing, depending on where you are. Again, take a look at all four of these. This product is positive, thus increasing. The product of these two is negative, thus decreasing. The product here is positive, and it's increasing. The product here is negative, and it's decreasing. Okay? If this helps you, you can thank Victoria. She was the one who thought of it. Okay, but again, it's one of the things that you just might pick up on by looking here. And on 2? Yeah, I don't know about that. I didn't hear anything come out of your mouth.
I told you that.
Did you?
Yeah.
I must have missed you saying that, sorry. I heard you say write it up. I got that part, but I meant the whole assigning positives and negatives. Alright, let's go on to the next page. Flip on over, please. The next part we're going to look at, we're going to study the effect of decay value. So take a look at your worksheet. You're going to have 3 functions there. You see them all? Y1, Y2, and Y3. Please graph those in Y1, Y2, and Y3.
Get it?
Again.
Why?
Man, Kobe last night.
Lakers win last night?
No.
Nah, they lost.
Yeah, sure, let's go.
Did they lose?
Yes, they're
I
gone.
didn't catch that in the game.
They
Wow.
didn't
It was
lose.
32-32.
They didn't lose.
Second quarter.
Everybody just had the same bad dream.
They lost.
They were dumb.
We had a bad dream.
Everybody had the same bad dream.
It was 32-32 in the second quarter, and that's when I
How do
checked.
you switch to your next class?
Yeah, it was.
Or do you just keep going down?
You don't grab them in different clocks, do you?
First one goes in Y1,
No,
second Y2. No, all the same plot. They're plotting them all together, guys. Simultaneous. Simultaneous at the same time. So put 1 in Y1, 1 in Y2, 1 in Y3.
Are we supposed to draw this on that paper?
How do you make the little black space?
It doesn't matter right now because your exponent just is an x.
Okay.
But if the exponent was something like x plus 2 and the exponent, you would need parentheses right here.
Hey, it's a something.
Good, very good. Draw a quick sketch on your graph, please, or where you have a little room there.
It looks like a
Just
river.
draw yourself a little sketch.
It looks like
It looked like a rainbow.
They
It's
on
sad.
them trying to-
Yeah, that's what it should be looking like, actually. Okay, draw yourself a little sketch of the 3. And try to be somewhat accurate with the sketch.
Like the Puma sign.
No, it does, actually. Throw a few more in there, and it would actually look closer to the Puma sign.
No Puma sign.
You don't see a Puma sign there?
You know the little
I
lines?
think it's just like
I see it.
I see the Adidas sign.
You strikes, baby.
He's square with tentacles.
Is that what you all kind of see?
Yeah.
A general shape?
Okay.
Alright, now, here's where you gotta start really thinking. Look at the next part, or look at the part of the graph as it goes to negative infinity. So, as it goes that way, to negative infinity. What do you notice is happening with all 3 of these graphs?
They're going to the right and up.
Wait, we're coming down.
Well, they're going to the right and they're increasing. They're all increasing, good. But I'm saying as I go that way, what happens to all of them? They all go in one direction, sure. What else?
They all go to negative.
It's like they're parallel. They're all going toward negative infinity. Well, what's happening to the curvature?
It's going up.
It's
It's
going
decreasing.
straight.
I mean, it's not a curve anymore.
What is it becoming more
A
of?
line.
Thank you. That's what I was trying to get at. It's
Oh,
flattening
I
out.
missed it straight.
Okay, it's flattening out. When something flattens out, what did we call that yet?
Is that a line?
And it's never getting to that spot, but it keeps
Asymptote.
flattening out. Good.
Asymptote.
That's your horizontal asymptote you're seeing there. So take a look. Here, put a little dashed line on your graph. Relax, please, whatever that is. Put a dashed line here. I don't want to hear you clearing your throat, that's why. Okay, put 3 dashed lines there. Now, try and look at your graph carefully. Somebody tell me, this bottom dashed line, what is that the equation of on my graph? If I look carefully at my graph, where does that represent?
2x minus
Okay, good. This is the graph of 2x, 2 to the x, minus 3. That's what this graph is right there that goes to that line. Now tell me, the horizontal line you see, the dashed one I'm showing you now, what would the equation of that horizontal line be?
0
We're all
minus
forgetting about this.
They're good. Oh, positive 3, right?
Is it what we just
0 minus 3.
Not 0 minus 3, not positive 3.
Wouldn't it be the number?
What's the question?
I mean,
Wouldn't it be negative?
0,
Wouldn't it be
What's the
negative?
question?
The question is this dashed green line at the bottom here, what is its equation?
Y equals negative 3.
Very good. Good job, Marcus.
Oh, yeah.
This is the line y equals negative 3. What is this line right here?
Y equals 2.
And what is the next line above it?
Y equals 6.
Where are you getting these numbers, guys?
Divide.
the second number and the whole number.
Yeah, that's the
What do we call this? Not the H, guys, not the H.
Okay.
It's decay. Look at the original function. Remember, that's the standard form. Is there anything else in the exponent with the x? Focus, come on, look up. There's nothing else in the exponent with the x. There is no h value in this problem. The a value is not even there. The a value is actually 1 here. It's not even shown. But the k value at the end is what's represented by my asymptotes. And if you look back at the notes, we look back at the front page, guys. Look back at the first page here. Remember for k we said it's the vertical shift, but it's also the horizontal asymptote. That's where this is coming into play now. So when we look at this graph here, we're going to see that each of these graphs, that's the first one. The second one was y equals 2 to the x plus 2. And this was y equals 2 to the x plus 6.
So is it positive or negative?
What do you mean it's positive or negative?
Positive or negative decay?
This is going up, so it's positive growth. Remember, decay comes closer to the x-axis. Decay drops toward the x-axis, whereas growth moves away. And we're going to write that in a minute, actually. Okay, we're going to fill in those spots. But again, the key points here are this. The k value is where the horizontal asymptote is, every time. So if you have any function, 2 to the x plus 7 minus 5, that means y equals negative 5 is your horizontal asymptote. So whatever is at the end of that function, what if there's nothing there at the end?
0.
It's plus 0. Well, what's the line y equals 0? It's the x-axis. Well done, sir. Good. Negative 3 is here. 2 is up here. Well, where's y equals 0? It's the x-axis, really. And if you go back and look at your examples from here, these did not have a k value, right? Didn't these all have plus zeros on the ends of them? They were all a bunch of plus zeros. And take a look. All of my asymptotes went to the x-axis, didn't they? This one went to the x-axis. This one came from the x-axis. This one came from the x-axis. So my horizontal asymptote for all 4 of these was just y equals 0. We just didn't mention it. But again, the horizontal asymptote is just the x-axis in this case. But when we get to the part that we're looking at, which is here, we can say that our horizontal asymptote, generally speaking, is at y equals k. The horizontal asymptote is at y equals k, whatever k is. So if k is 7, it's y equals 7. If k is 30, it's y equals 30. So whatever you get for your k value, whatever you see in that equation, that is your horizontal asymptote. Okay? That is your horizontal asymptote. Now, what I would like to do next is talk about end behavior and how we can relate this. So let's do this. We can also know end behavior of growth functions. And let's take a thought for a second. My growth functions, I have 2 possibilities for growth functions. Let me clear the ink on here actually real quick. Okay. I have either positive growth or I have negative growth. And that's where that trumpet comes in again. Same shape. So this is positive growth and this is negative growth. And take a look at this. Both of these functions do something at the edge. What is it called when you go to different directions? What do you do? Split up. What's the fancy word for that?
Separate.
Separate.
Not fancy.
Like depart. So that's a D. Close. The road has a. When the roads come together, what do you have?
Diverge.
No, collision.
Close.
That's like a
When the roads come together, what do they have?
Diverge.
Diverge. Diverge. That's the word. Not divergent, but diverge. So these 2 graphs diverge, right? They go away from the x-axis toward the right.
What's how that Robert Frost poem go?
I don't know, but let's go back to here for a minute. Give me a minute. We can go back to it. When the roads diverge.
Nah. It's the Robert Frost poem.
So, as x goes to infinity, what does that mean again? Goes to the
Right.
right. Again, x to the right. X can only go right or left. And if it's positive infinity, it's going to the right. As x goes to the right, what happens to my graphs? Either they go up to infinity or
They go down.
it's a negative infinity, right? So the y value goes to either plus or minus infinity there.
So that's still the one we used to do.
For positive or negative growth, as x goes to the right, we see that our graph either goes up to infinity or it goes down to negative infinity, depending on the concavity.
So right now there's a bunch of positive.
Well, the ones that we were doing were all going to positive, yes. The ones that we were doing were all going to positive.
No, I was gonna ask what you don't want to put that, but you can answer the question.
Now, the next thing I want you to notice, though, is this. Be careful here. As x goes to negative infinity, so as I go to the left forever, to the left, look at your graphs. Each of them go to a different value, don't they?
Mm-hmm.
What is the height of the function that it goes to each time? Give me the examples, the 3 examples you have there.
6, 2, and 3.
6, 2, and negative 3. Remember, this one here looked like this, where it went to y equals 6. This one here looked like this, where it went to y equals 2 on the left. And this one here looked like this, where it went to negative 3 on the left. Pick up whatever that was that just fell, please. Now, what you're noticing is each of these values, as you go to the left, go to different heights, right? Again, this part of the graph, this goes to the height of 6, this goes to the height of 2, this goes to the height of negative 3. So how can I write that? I can't write 6, 2, or negative 3 because it could change, right? What is it based on?
Don't you have to write it in that form?
I'm writing y goes to what? That's my question here. What can go in that blank? Look at the 3 examples. The first example, when I went to the left,
Negative.
what's that?
So it could be the same thing, plus or minus.
Not plus or minus again.
Greater than or less than 0.
Let me start over because we're not seeing this clearly. The first graph we looked at a minute ago was 2 to the x plus 6, and this is what the function looked like. Okay? The second graph we graphed a minute ago went to positive 2 and looked like this. The third graph was down to negative 3, and it went like this. And what I'm trying to ask you guys is this. Each of these values, or each of these functions, this function goes to 6. It'll ride along 6. This function will ride along 2. This function will ride along negative 3. Do you see that? Everybody see that so far?
Yeah.
So this one goes to 6, this one goes to 2, this one goes to negative 3. 6, 2, and negative 3, where do they come from? Which parameter? A, B, H, K, where do they come from?
Okay.
The K value. Again, the K value. Remember the standard form that we started today with was this, right? And it's this K value at the end that gave us the 6. This is K. This is K. This is K. So I can simply write that instead of saying, a certain number, because I don't know what the number is. What if the function, instead of saying 2, negative 3, or 6, said 5? Then it would go to 5, wouldn't it?
Yeah.
So what can I write holistically? K. Very good. Just put a K there. Because whatever K is what the function is going to go toward. If K is 7, it'll go to 7. If K is 8, it'll go to 8. If K is 25, it'll go to 25. So we can write this relationship here for end behavior as a function of K, really. So whatever K is dictates the end behavior there. Now, to go into a little more detail for the next one now. And this is where it's going to get a little even more tricky here. For this part, what does the K look like now? Decay. Not K, the variable, but growth versus decay. Start up here, and where do I go?
Down.
And is it going to be concave up or down?
No, concave up.
Concave up. That's the K, right? It's concave up, even though it's decreasing. And I should not curve back up. That's incorrect there. I should make sure I'm clear that I do like that. That is exponential decay. That's what we call positive decay. Remember, negative decay was the next one. That looked like this. So it was remember the trumpet we just drew a minute ago? It's the trumpet, but it's just kind of reversed now. Okay, the last trumpet looked like this. So, a minute ago, we had this statement here. And we had this. Okay, that's what we had a minute ago. And I know it's on your paper, but it's not on mine right now. So, what do we notice for the exponential decay functions that is different or similar, either one, to what we just wrote down for the exponential growth?
It's still going
The
to
beginnings are the
x-axis.
same.
It's always as x goes to infinity, x goes to negative, right? Yes. Always. But what are the y values going toward now?
Positive.
The y values?
Look at
I
what we
thought
wrote.
it was K.
Oh, it's going to.
Again, we determined this for growth, right?
Infinity. You're not going to positive.
As x goes to the right for growth, it went up, right? But now take a look. As x goes to the right, what's happening to the function?
Oh.
X is K.
It's going to a positive infinity.
You're not saying it right, Marcus, but you have the right answer. It's decreasing, or it's going toward the x-axis, right? In this case, the x-axis is like our k value. If you do a bunch of these graphs together, if you graph ones that look like this, okay, and this was, let's say this is y equals 2 to the x, or no, not 2, 1/2 to the x. This is y equals 1/2 to the x plus 4. Y equals 1/2 to the x minus 3. What we're noticing is that now on the right side, each of these are going toward the asymptote. Whereas last time it was reversed. It was on the left-hand side. So Marcus made a good comment that all that's happening is as x goes to the right, or toward positive infinity, y now goes toward k. Again, look at what's happening. The graph is settling out as it goes to the right. It's becoming asymptotically closer to the asymptote itself, or to the line, in this case, y equals, this would be 4. This line here would be y equals 0. This line here would be y equals -3. So every time you go to the right for decay, it's flattening out to whatever the k value is. What about when I go to the left, though? What's happening? That's where it's going to plus or minus infinity. So what can you say about the end behavior of decay versus growth? It's just the opposite, or just flipped, right? It's just flipped. Take a look. Again, when it goes to the left for decay, and look at your graph, as I go to the left, it's going up to positive infinity, or it's going down to negative infinity. So that's as it goes to the left. But as it goes to the right, it's going toward the k value. And it was the reverse for growth a minute ago. Okay, it was the reverse for growth. So it's good to know about our end behavior, because we're going to be able to determine what type of function it is by looking at the end behavior as well. Okay, it will help us determine the type of function as well. Questions on this? One more thing to do before we close for today. Okay? Let's take a look at what you see on the next part, and you're going to be asked to graph all three of these. Okay, all three of them again. So go ahead and graph all three. Put one in Y1, one in Y2, and one in Y3. Give me that. I know, but you need to get to the last part. Finish it, and then maybe I'll let you go for a minute. But you go every day, yeah. I gotta start. Just finish this next show, okay?
X plus 4. But that has to be in
Yeah, notice, guys, look at your exponent. It's two parts to it now, x plus 4. You need parentheses around your exponent. Again, you need parentheses around your exponent. So your keystroke for the first one would be
2 caret parentheses x plus 4.
that would be Y1. That's what you're going to type in for Y1. Again, don't forget your parentheses around only your exponent. Only your exponent. And then please zoom 6 it afterward. Relax. Be nice to each other, guys. Stop. Very good. That's the first thing you notice. They all come off the same horizontal asymptote, right? Aren't they all with a +2 at the end? Everybody see these +2s here? Doesn't that tell me that the horizontal asymptote is going to be y equals 2? So I know already what I can do. Let me move my graph over a little bit. What I can do is draw the line y equals 2, and notice that the first one goes like this. The second one goes like this. And the third one kind of goes like this. Would you agree?
Yeah.
So which way have these ones been shifted? To the right or left, right? Or what do we call that? Horizontally. But is there any vertical shift difference at all?
No.
Because look, all the k values were 2. So there's no difference in the vertical height. But look at your exponents now. X plus 4. X plus 4, that's this one over here. Because plus 4 means shifted to the left. Remember? You do the opposite for h. Here, this is just simply the graph of y equals 2 to the x plus 2. This one, though, is y equals 2 to the x minus 3 plus 2. And notice, when you have a positive here, it shifts to the left. Because remember, it's x minus h. When you have a negative here, it's shifted to the right. When you have nothing there, there's really a plus 0 here. So that's like your parent function. Okay, there's really a plus 0 up here. So this is like your parent function right here. This shifts to the left because it's a plus 4. That shifts to the right because it's a minus 3. Okay? Again, notice they're all coming off the same asymptote. And if you look at my notes later online, you'll see that I even showed the asymptote here. They're all coming off the exact same asymptote in your graph.
Is there any way you can like
Any way you can.
see that?
You can't see the horizontal one unless what you do is you just change your window. And if you change your window to like -20 for the x min, you'll see them converging on the same line. That's all you'll see, but you won't see an asymptote. Okay. Again, so the exponent indicates the horizontal shift, whereas this end value indicates that vertical shift that we're looking at. Okay. Tomorrow we're going to pick up with the 2 questions. Okay, those 2 questions, and then we're going to go right into concept 54 tomorrow as well. Okay, just to give you a little preview. We're going to pick up with those 2 questions there and go right.